Hello and welcome to this poster presentation made by Kim Jensen, a robotics student from Aalborg University in Denmark. In this presentation I will cover the project of determining dendrometry using drone scouting, convolutional networks and point cloud processing. This project was created together with the rest of my student group, which weren't able to be here today. The purpose of this project is to reduce the amount of pesticides used in orchards. The pesticide reduction provides both ecological and monetary benefits, and as we found them to make up approximately 30% of the cost in orchards around the world. One of the ways to reduce the number of pesticides used is through precision agriculture, where you try to find the characteristics of the orchard. Information on where the trees are planted and their size and shape can be used to target the spraying of pesticides more precisely and thereby reduce the amount of pesticides used. The goal of this project was therefore to find a way to automatically find the location of trees in an apple orchard and calculate the dendrometry of the trees. As the project served the function of a proof of concept, we chose to delimit the dendrometry estimation to only the height of the trees. While RGB-based convolutional networks have been used for detection and classification in the field of horticulture, then CNNs are not commonly used for collecting dendrometry. On the other hand, point cloud data is not widely used in the field of horticulture, but research has been done in the area of dendrometry estimation using point cloud processing methods. Despite the high detection rates and relatively accurate estimation of dendrometric data, the proposed methods are not applicable because they are based on expensive terrestrial laser scanners. However, cameras such as Intel RealSense are cheap alternatives for point cloud gathering and could potentially be used for detection and dendrometric data estimation in the spraying solution. Therefore, the objective of this paper is to explore the possibilities of apple tree detection and dendrometry estimation at an orchard by comparing results of both RGB and depth data. The main contributions of the proposed system are a performance comparison of point cloud processing and convolutional networks for both detection and height estimation of young apple trees in an orchard, and then also a simulated proof of concept for visualization of the automated mapping and data gathering solution proposed by the paper. So our proposed method is the use of a drone equipped with an RGB-D camera for both locating the trees and calculating the dendrometry. Drones have the advantage of being able to fly from a top-down view of an orchard and thereby being quite flexible in use. As the project seeks to find an optimal way of performing precision agriculture, using the RGB camera allowed us to easily record both RGB and depth data at the same time and later compare the methods which we used for handling these data types. The proposed method for the project can be seen down here in the bottom left figure. And initially the drone would fly above the orchard and then using these depth capabilities of the camera create a map which will have the position of each of the trees. As the canopies of trees generally blend well with grass, the normal RGB images were not considered viable for this step. Using the depth data, a threshold was set to remove the ground plane from the orchard. A clustering algorithm could then be used to find the trees in an orchard. Using the map generated in this step, the drone could now be flown between the rows of trees. This allowed us to record data from the side view of the trees, which could then be used to calculate their dendrometry. However, having the drone simply speeding by the trees wouldn't give any usable images. So instead, an algorithm was developed with the purpose of creating waypoints next to all the trees, such that the drone could hover in place and get more usable images. The algorithm works by using the map of the orchard, generated by the drone during this first flight, which you can see down here in this image. And then the algorithm finds the distance between the center of the trees and clusters the trees together into rows. And then hereafter the waypoints are created next to all the trees to ensure that the drone could take usable images. And once images of the trees are acquired, then both RGB and point cloud processing is done to calculate dendrometry data of the trees. In this project, YOLOv3 was used for IGB processing, while the point cloud library was used for point cloud processing. The YOLO CNN was pre-trained on the COCO dataset, and transfer learning was used to train YOLO to recognize apple trees instead, where we used 900 images taken at the orchard. The processing of the depth data started with filtering, downsampling, and smoothing of the data, and then afterwards a region of interest was defined, and all points outside of this region of interest was removed. Next, ransack is used to identify the biggest plane in the data, which is then removed as we assumed it to be the ground plane of the orchard. And then finally, the remaining points are then clustered such that each cluster represents a single tree. And this is done based on an algorithm based on the Euclidean distance between points. The tests of this project were performed both in simulation and in the real world. The navigation tests and estimation of tree position were done in simulation. A figure of the simulated environment can be seen here in the top right corner, where the top part of the figure shows the simulated environment and the bottom part of the figure shows the drone that has mapped the trees, and this is done using an octomap. As we can see here, then all positions of the trees in the simulated test were determined within a 5 centimeter of precision. The tree detection was tested with two convolutional networks, and this was the YOLOv3 and the YOLOv3 Tiny. And it was also done with this point cloud processing method. To compare the results of these tests between the two approaches, then the precision and recall were calculated. For the CNNs, then the traditional calculations of precision and recall were used, but for the point cloud processing, then the terms of true positives, false negatives, and false positives have been slightly adapted. Here we consider true positives to be clusters containing a single full tree model, which can be used for estimation of dendrometry data. We consider false negatives to be the full tree models which are visible in the input data, but that were not segmented into any cluster. And finally, any other type of cluster will be considered a false positive. And as can be seen by the table here in the middle, then the YOLOv3 architecture and the point cloud processing method proved to have the best results. Here the YOLOv3 with an intersection over union of 25 showed a 78.04% of average precision, while the recall was 81.42%. For the point cloud processing method, then the average precision was 76.72%, while the recall was 86.2%. After the detection of trees has been made, the height of the trees has to be determined. Here the methods of YOLOv3 and point cloud processing again proved to be the best results for determining the height of the trees. So here YOLOv3 had a mean error in the height estimation of 20.6 centimeters, while the point cloud processing had a mean error of 20.4 centimeters. In this bottom left figure, you can see the output from the YOLOv3 network, where the network has detected the trees and has placed a bounding box around them, and then the height of the trees is then estimated, and this estimated height can be seen up here in the top left of the boundary box. When looking at the figure down here in the bottom left, then you can see that there's a lot of ground vegetation and also a forest in the background. And that's in all of the data that which we've used. And here specifically the forest in the background presented a problem for the YOLOv3 network, where parts of the forest were misclassified as apple trees. For the point cloud processing, then this ground vegetation down here could sometimes also cause some misclassifications. However, in general, both methods showed the potential to be able to detect trees and extract dendrometry data. One of the things that affected the testing of the CNNs and point cloud processing methods were the seasonal changes during the development of the solution. This caused the apple trees in the orchard to drop their trees prior to testing. So if the testing was performed with a data set of trees which had the leaves, then the mean error in height estimation is expected to drop. Additionally, to increase the robustness of the CNN algorithm, the dataset should be expanded to contain images throughout all seasons of the year, so that the proposed solution could also work all year round. In conclusion, this project showed that it's able to fly a drone automatically over an orchard, map the environment, and then extract dendrometry data from the trees. Both methods used during this project showed that there are viable options for automatic collection of dendrometry data of trees, as they detected all trees at least once during the dendrometry testing. In general, the point cloud processing method showed better results when compared to the UWV3 method for detection precision, but in general it trades off processing time. Further research could be done on developing an approach that combines the UWV3 and the proposed point cloud processing method. So, for example, if the high FPS is needed, then UWV3 can be used for fast detection of trees, while the point cloud processing can perform more precise detection at lower FPS. Additionally, the dendrometry estimation could be expanded to include other parameters like the diameter of the stem and crown, or for example the tree shape. This was the project of determining dendrometry using drone scouting, convolutional networks, and point cloud processing. Thank you for listening.